Hi, everybody. I have caught COVID again for the second time. Uh, I caught it at the exact same time last year, right at the middle of September. Um, I'm not really enjoying it. So I'm recording this video so that you guys can take some notes in your new study guides. Hopefully, I'll be ready to come back on Tuesday, but we'll see how things go. Hopefully by now you have a copy of your new study guide. If you do not, they're in a large stack on that center front row table. Um, you should go get one of those right now. Make sure you have the whole study guide so you have a cover page, a blank back page, and then there should be, I think, 13 pages in this study guide, but I could be wrong. So check and make sure that that's accurate. But again, you have the whole thing if you have a cover page and a blank back page. We're going to look at a few different things today. I'm going to share my screen. Right, here we go. So we're going to begin with a few basics, a little bit of review from last unit on decimal places and accuracy of tools, and then we're going to get into graphing. So my goals for today are to use graphs to analyze data and to use the acronym DryMix to label particular variables in graphs. I have this video here that I found that popped up on my For You page on TikTok. And if you don't know this by now, TikTok definitely listens to everything you say and everything you do on your phone, and it knows what to show you and what you think will be funny. And me being a physics teacher and just having talked to you guys about quantitative and qualitative measurements, this video came up and I laughed pretty hard. So I wanted to show this to you really fast.
There's butter. There's extreme butter. Some butter lovers. Some ultimate butter. And movie theater butter. There should be a more empirical way of measuring butter.
When he says empirical, he means quantitative. So I thought that was kind of funny. All right, moving on then. So here's our cover page, Scientific Destiny. Destiny is kind of a play on words, and you'll see why I did that in a sec. What I wanted to do first is on page 2. Down there at the bottom, there is a little table with 3 rows: mass, volume, and density. I would like you and your partner to take maybe 30 seconds to a minute and fill in those 2 rows. Those should be reviewed because we know what mass and volume are. Skip density for now. We will come back to that later. I'm going to put 45 seconds on a timer, and then we'll come back in those 45 seconds. Again, you and your partner fill in those 2 rows. Ready, set, go. Yeah, if there are still a good number of you working on it, the sub can pause the video until you guys finish this up. All right, for mass, we should have a symbol of M, a description. I think we said last week that mass really describes the amount of matter that an object contains, and you could have said the amount of stuff, the amount of particles, the number of atoms. Those all really communicate the same message. We don't have a formula yet for mass. We'll get to that later. Our measuring device for mass is a balance scale, and our SI unit for mass is kilogram. Now, I said last week, kilogram is used as the SI unit instead of gram for historical purposes, but because kilograms are rather larger, they're about 2.2 pounds. We actually, in our class, won't be really measuring anything that large. We will instead be measuring things that are much smaller, and therefore gram will be the more appropriate unit. I wanted to get that out of the way. But again, SI unit is kilogram. We're going to be using more grams than anything. For volume, our symbol is a capital V. Our description is the amount of 3-dimensional space that an object takes up. Our formula, we don't have one for that yet. Actually, no, that's not true. We might. We talked about a formula last week. If you're measuring the volume of a solid cube or a some kind of rectangular prism, then you can multiply length by width by height. So that's something you can include here. There also are other formulas for other shapes, but we'll just stick with that for now. Our measuring device for volume, if it's a liquid or a small object that can be submerged in a liquid, then we're going to use a graduated cylinder as the measuring device. If it's a large, solid, cubical, or rectangular shape object, then we can use a ruler to just measure the dimensions and multiply them together. So graduated cylinder is the most important one, but you can also include ruler. Our SI unit for volume is liter. And similar to with the mass, we probably won't be measuring any volumes that large. And so the more appropriate unit for us during this chapter, during this unit, will be milliliter. So we'll get lots of opportunities to measure masses and densities. All right, we're actually going to go all the way to the back to page 13 first. This is just a little bit of a review from the first unit on decimal places and measurement accuracy. I'm going to read this top part out loud. Excuse me. It says the volume of a cube with dimensions 23.0 centimeters, 14.971 centimeters, and 12.73 centimeters can be determined using such things as a calculating device, website, or app. Entering those numbers together and multiplying together into a calculator would yield an output answer of 4,383.35909. However, that number, cubic centimeters or milliliters, is not considered an acceptable volume in science based on that given data. The reason being is this answer has 5 decimal places in it, but the numbers that were used to calculate it did not. And I realize that the numbers don't quite match. That's a typo on my part, but the point being, the numbers that were used to calculate it did not have more than 3 decimal places. This answer, however, does have more than 3. And so that's a problem for us because we can't record more decimal places than the numbers that we were using to solve it, because how can we? Even though the calculator gave us some more decimal places than we originally had, that doesn't mean that we, as the measurer or as the person working with these numbers, are actually confident as to what those numbers are. So A says, what is the guideline that you will follow to determine how many decimal places to include or exclude from your calculated answers? I think I told at least a couple classes this last week, but I might not have told everybody, which is why I included this page. Our guideline, or the rule we're going to follow, looks something like this. The accuracy of the answer must be the same as the least accurate number used in the problem. Okay, I'll give you a minute to write that down. But essentially what we're saying is it's a similar notion to a chain is only as strong as its weakest link. We can't record more decimal places than the least accurate number that we used to solve that problem, because we aren't really sure what those numbers are. Even though the calculator tells us that they have a value, we wouldn't be able to measure them. And so the overarching kind of guideline is we only want to record numbers, digits, decimal places that we're actually confident in. And how do you know if you're confident in them? Well, it comes from the problem, the numbers that were used in the problem. So for example, this number up here had 5 decimal places in it. That is too many. We're not actually confident in all of those. If we go back to each of the numbers used in the problem, this one had 3, this one had 2, and this first one had 1. And so according to the rule, we can't be more accurate than the least accurate number we used in the problem. This number we should round it to 1 decimal place, because that was the least accurate number we used. So I would round that 3. I would probably round it up to a 4. So my final answer would be 4,383.4. Part B says, how does this guideline above relate to your previous work with rulers to the final figure? And it's really exactly the same thing. Decimal places are a reflection of the accuracy of the tool and the confidence that we have in the measurement. So our calculations cannot be more accurate than the tools that we use to get them. And so often the numbers that are given to you in a problem, you yourself did not measure, but you have to assume that they came from a measurement. They didn't just come from nothing. We have to assume that they came from a tool that has a limited amount of accuracy. So our calculation, our answer also has a limited amount of accuracy. Once you get done with part B, this last 2 problems here, they're pretty easy, but it says practice answering the following questions as you would for a test or a quiz. And it says to use the information on page 0, which is the reference page, the very first thing in your study guide. I have included a little screenshot of the relevant information right over here. Whenever you take a test in here and you are recording a number as an answer, what I do is I break the answer down into 3 parts. And I do this for a few reasons. One is to make sure that you are constantly aware of accuracy and how accurate your number is allowed to be. The other reason I find it useful is it helps in the grading process. It kind of helps you to break this thing apart. I think it maximizes the number of points that you can possibly get. And it's useful for me too in grading. So let's try this. Number 1 says, find the volume of the cube below. Each of the dimensions is given, and you can see that each of these numbers has a different degree of accuracy. This number here would be the most accurate. This one here would be the least accurate. So when we answer this problem, we should first do the math, right? If we want to find the volume of any kind of cube or rectangular prism shape, we multiply these dimensions together. 14.2 times 14.22 times 14.222. What I'd like you to do is to do this first before I show the answer. The sub can pause the video for 30 seconds or so. I would like everybody to get their own calculator. I'll say that one more time. Everybody should get their own calculator. Don't share a calculator with your neighbor. Get your own. So the sub can pause for a few seconds while you guys go get those. Okay, welcome back. You should have a calculator in front of you. You should have punched these 3 numbers in and multiplied them together. When I did that, this was the number that popped up. And it's very similar to the problem we faced up here. There's too many decimal places here. I can't record all of them. And so this is where things become nice. If I were to follow the rules over here for how to write this answer down, 1A just says whole number value. All that means is, what is the value of the number to the left of the decimal point? And I don't want you to round here. I don't want you to include any decimal places or a decimal point. I just want you to write the number that is to the left of the decimal, which in this case is 2,871. That's it. That's all you have to do for A. Anytime you have a problem with a numerical answer, that's what A is asking for, just the whole number. Part B says the number of decimal places that you have in your answer. Now, that doesn't mean how many decimal places did the calculator tell you. It means how many can you actually have? How many are you allowed to have? And remember, the rule says that we must be as accurate as the least accurate number used in the problem. This problem had 3 numbers. This one over here is the least accurate with 1 decimal place. And so for 1B, I'm just going to say 1, meaning 1 decimal place is the number that I'm allowed to have. What I don't want you to do is to take the actual value of the decimal and round it and put it for part B. So I don't want you to put, 0.7 or 0.8. That's not what I want. The reason I like that is because sometimes we have different rounding rules. I've seen people that learn different rounding rules in earlier grades in elementary and middle school. And so I don't want to have to deal with, you rounding a little bit differently than I did. I don't see a lot of value in penalizing you for that. So again, for any part B on these numerical problems, I just want you to tell me how many decimal places you're allowed to have, not the value of the decimal itself. This last one, part C, just says, what is the SI unit that you used? In this case, because we multiplied 3 dimensions together that each had a unit of centimeter, then the volume unit we obtained would have a unit of cubic centimeters, or centimeters to the 3rd power. And this will depend on whatever problem you're working with. It could be meters or seconds, it could be kilograms. You're going to see the units we start dealing with in physics kind of get bigger and longer, but whatever it is, that's what you put down here. I don't want any numbers for part C. I just want the unit. And so this would be the correct way to answer this if it showed up on a test. Let's do the same thing, but for number 2. I want you to first do the math, which is just find the volume of this rectangular, this overly accurately measured cube. And then I want you to answer it according to the rules for a test, A, B, and C. The sub will pause the video here for 30 or so seconds. You'll write it down your answer, and then you'll compare it to mine when you come back. Ready, set, go. Okay, the sub should have paused while you guys worked on it. If not, pause now, but I'm about to show the answer. When I punch it into my calculator, this is the number that I get, 32 point blah, 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 a whole lot of decimal places. But I have to be conscious of that. So for 2A, just wants the whole number, so it should just be 32. No rounding, no adjusting, just 32, whatever's left of the decimal. Part B, how many decimal places am I allowed to have? Well, the least accurate number of these 3 is this one over here, which has 4 decimal places. And so that's how many I'm allowed to have in my answer. 4, no more than 4, no less than 4. And lastly, C, what are the units? Each of these numbers was measured in meters, so multiplying them together would give a unit of meters cubed, or meters to the third power. And so that's how you would answer that on a test. Hopefully by now you can see that if you answer these correctly, you get 3 points on these problems instead of 1. Additionally, let's say you get to this problem and you have no idea what to do. You don't know how to find the volume, you forgot you're supposed to multiply these together. Well, then you'll likely get part A wrong. But you shouldn't get part B or C wrong because you know this rule and you know the units. The great thing about units is you don't have to memorize them. They're all on the reference page. You just have to look it up. So anytime I give you a numerical problem, you should automatically get 2 out of 3 points without even knowing what to do because you know the rule for decimal places and you know where to find units. So that's another reason I kind of like it. It gives you the benefit and allows you to get the most number of points. Right, we are going to move on. We're going to head back to the front portion of the study guide. I believe this is page 4, so head over there really fast. On page 4, we're going to start this unit with a little bit of discussion on graphs. Excuse me. Right up here at the top, it says graphs are a tool used in science to analyze data and determine relationships. And I wanted to pause really quickly and remind you that on this page, this is page 2 at the top, each of these down on this left side are the major components of this study guide. Your job is to fill in what cross-cutting concept you think was featured, which you can find on page 1. I think page 1. Hopefully I'm right. You're also supposed to fill in which science and engineering practice you think was featured. And so right there, this is the science and engineering practice that is determined, analyzing and interpreting data. So if I were you, I would write that down right now. The disciplinary core idea, you can also fill in once we kind of get done with this page, because you'll have an idea of what was the big idea, what was the thing I was supposed to learn when going through this. The cross-cutting concept, that's kind of up to you. You get to choose what you thought the biggest cross-cutting concept that was featured was. So maybe you thought it was patterns, maybe you thought it was cause and effect. It can be anything you decide. So I wanted to give you a chance to write that down. I'm going to continue reading on the top of page 4. Oops, sorry. It says line graphs are used to show how manipulating one piece of information relates to how something responds. Down here, I have a Google Doc, and I wanted to show you just because this was one of the labs, one of the experiments I had to do when I was in college. I was in a lab, and they gave me a bunch of materials, and they said, you can decide what you want to do with it. And so I decided to conduct some investigations with light and light intensity, and I just wanted to show you just kind of the depth of how much data I have here. I'm just kind of scrolling down, and I'm just going to keep scrolling until I get to the bottom here. You can see here there are 700, I think I've just subtracted 2. So there are 795 times 2 data points just in this one trial. And I conducted probably dozens of trials for this experiment. When we have really, really large quantities of data like this, it becomes difficult to actually glean any useful information out of it. And so that's why one of the most important practices that a scientist can engage in is graphing and ensuring that they know how to graph, because that's really the only way we're going to be able to figure out what the data means and if there's anything significant to glean from it. In this box, the most common graph we will use in here is line graphs. Not to say that we won't ever use any other type of graph, but I found that line graphs are generally the most useful for us. And they're really, really good at comparing 2 variables. And you can see in here, these variables have names. They're called the independent and the dependent variable. One of the variables is manipulated or changed, meaning we go in as the person in charge of the investigation and change this variable, manipulate it somehow. The other variable, the dependent variable, is the one that responds, or at least we're trying to observe how it responds to whatever we did to the independent variable. Right down here, it says describe how dry mix will help you remember this information. And it's kind of a lot of information. Which variable is which? How am I supposed to know? Well, I found a really nice acronym to kind of help you out. So in this kind of blank space down here beneath where it says dry mix, I'd like you to draw this. First, draw a little graph with just an upward axis, a vertical axis like this, and a horizontal axis like this. We want to label these 2 axes according to that acronym, DRYMIX. The D stands for dependent, the R stands for responding, and the Y stands for y-axis. Down here on this horizontal axis, we'll label it M for manipulated, I for independent, and X for x-axis. So this acronym kind of tells you how to remember what variable goes where. Whatever variable you are changing, manipulating, that's the independent one. And you're always going to want to put that on the x-axis. Whatever variable is responding to a change in the other variable, that's the dependent variable, and you're always going to put that on the y-axis. Dry mix. Just a nice acronym to help you remember what goes where. The sub can get a quick little poll just to see how you're doing with this, with writing this down. If you need more time, they can pause it. If not, I'm going to move on to the next part. These problems are just some practice, just to see if we kind of get what I'm trying to say here. So I'll do number 1, maybe number 2, and then I'll let you guys kind of look at 3 through 8. Number 1 says, what is the effect of diet and regular soda on blood sugar levels? So our job is to identify which of these variables is independent and which is dependent. Remember, the independent is manipulated. In this question, what is the thing that I, as the investigator, is changing? I think it would be the type of soda. I'm comparing diet and regular soda. So that would be my independent variable, type of soda. My dependent variable is whatever is responding to a change in that type of soda, which in this case would be blood sugar levels. So that would be my dependent variable. Number 2 says, how does phone use before bedtime affect sleep? Same question. What is being manipulated? That would be phone use before bedtime. What is responding to that change? That would be sleep. So maybe you could say amount of sleep or hours of sleep or whatever you think is most appropriate for that. Okay, at this point, I want you to try to do the rest of these with your partner. You talk to them, write down your answers. What's the independent and dependent variable? We'll come back and talk when you're done. The sub can pause the video now and give you some time. Okay, you should have looked at these last 6. How well do different plant species tolerate salt water? I would say the independent variable is the different plant species. Actually, let me read that again really quickly, because sometimes they're a little ambiguous. Yes, I think the different plant species is the independent variable, and then the tolerance would be the dependent variable. So as far as what does tolerance mean, do they thrive? Do they grow? Is their growth stunted? Do they die? That would kind of be my dependent variable. Because the salt water, you might be tempted to say maybe salt water should be the independent variable, but I don't think so, because salt water isn't actually being changed. It's the plant species that's being changed or manipulated. Number 4 says, do tomatoes grow faster under fluorescent, incandescent, or natural light? Independent, manipulated, or changed, that's the type of light. Dependent would be probably growth speed of growth time or speed, whatever you want to call it there. Number 5, you are assigned to determine how much liquid different brands of paper towels can hold. So different brands of paper towels, that's what's being changed. That's the independent variable. And the dependent or responding would be how much liquid they hold. So probably volume of liquid, or maybe mass, that would work too. Number 6, is consuming caffeine something which can affect a person's appetite? The thing that we're changing would be the caffeine consumption. So maybe how much caffeine you consume. The dependent variable would be the thing that responds to that, which is your appetite. Number 7, do stressful experiences increase the likelihood of headaches? Independent variable, the thing that changes would be stressful experiences. How many stressful experiences? The dependent variable would be headaches, or the likelihood of getting a headache. Number 8, will potatoes sprout better in the light or in the dark? Independent variable would be light versus dark. Dependent variable would be the sprouting, or the amount of sprouting the potato has. Hopefully you kind of get the hang of this. Some are easy, some are not so much. But and I want to make clear, the reason these are here is just to give you practice. I'm not really going to be, throwing random investigations at you. We're going to be the ones doing the investigating. So it's up to us to decide what's independent and what's dependent. One more thing I wanted to mention at the top of this page is whenever we graph or whenever we title a graph, we always want to title it in this format: dependent variable versus independent, or Y versus X. So in the case of number 1, I would title this graph blood sugar levels, that's the dependent, versus type of soda. That's how I would title the graph. Number 2 would be titled amount of sleep versus phone use before bed. That's how I would title those graphs. One more thing before I give you a little bit more practice with this is when we decide on, when we graph data as line graphs, or in this case as scatter plots, but really the same thing, we like to look for patterns. patterns, hint, hint, or relationships, meaning does changing the independent variable on the x-axis actually have an effect on the dependent variable graphed on the y-axis? And many times they will. This first scenario highlights one case where as the independent variable increases, the dependent variable, as you can see in the graph, also increases. Both increase. Number 9 says to give an example. You can probably think of many examples. Just one off the top of my head. The harder I push a stationary object, the more it speeds up. That's a positive relationship. The bigger force I exerted led to a bigger increase in speed. So that would be an example. The more water I give my plant, the more it grows. Positive relationship. So write down an example there for number 9. Conversely, another thing that could happen between two variables is a negative relationship. You can see here that as the independent x variable increases, gets bigger, the dependent variable actually gets smaller, it decreases. We call this a negative relationship. It says to give an example. Again, you can probably think of many, many examples. Maybe the bigger the tread on my tires, the shorter the stopping distance when I hit the brakes. That's a negative or inverse relationship. You can think of lots of different examples there. Not lastly, but another thing that could pop up between two variables is a constant relationship. This one says, as the independent variable increases, the dependent variable, you can see that it doesn't change. It stays, and I put relatively constant just because a lot of times when we look at data, the data points aren't all going to fall perfectly on a straight line. They might vary a little bit, but if we don't clearly see a trend upward or downward, then we're probably going to err on the side of it's constant. Give an example of a constant relationship. Oh, let's see. No matter how much I could say, the more I yell at the TV, my football teams improve. My favorite football team's performance doesn't change. That's a constant relationship. It doesn't really have anything to do with it. So yeah, there's an example for that one. One more note over here. Sometimes, not all the time, but sometimes a positive relationship is also referred to as a direct relationship. So you can write that word right over here, direct. Similarly, a negative relationship is sometimes referred to as an inverse relationship. So you can write that word here, inverse. The last little example down here says no relationship. I want you to pay attention to this because a lot of times we get this confused with constant. In this example down here of no relationship, you can see that as the independent variable gets bigger, the dependent variable does change, but it does not change in any predictable manner. I cannot confidently say if I make any sort of change to this variable on the x-axis, then this is what's going to happen to the y variable. I can't make a prediction. And that's kind of the big difference between no relationship and constant relationship. With a constant relationship, you can make a prediction. With no relationship, you can't. So I'm actually going to walk back my example here. Maybe my example would be better suited for no relationship. The more I yell at the TV, my favorite football team's performance is unaffected. It will vary up and down, but it is not dependent on how I yelled at the TV. Maybe a better example for a constant relationship would be, the more I eat spaghetti, the rotational period of the Earth stays the same. Just a random example, but that feels a little bit more constant because I can eat as much spaghetti as I want. I'm really not going to affect how long it takes the Earth to rotate once. So there's maybe a better example. I'm glad we talked about that. Okay. That kind of does it for this part. I'm going to move on, pause the video if you need a little bit more time. Number 12 down here says to create a scenario that could be explained by this data. I'm going to give you a little bit of time to make something up. It's totally up to you. It can be whatever you want, but it does say to make sure, sorry if you can see this, it does say to be sure to label the axes and title it. So whatever your changing manipulated variable is, put that down here on the x-axis. Whatever's responding to that change, put it on the y-axis, and then title it dependent versus independent, y versus x. I'll give you some time to do that. The sub can pause the video. Okay, whatever scenario you created for this, it's totally up to you. I'm not super picky about it. I just wanted you to think of something. All right. What we're going to do now is just some practice with this, some more practice, and I found some interesting graphs that I think you'll enjoy. What we're going to do is we're going to do this with whiteboards. These examples are not in your study guide. So if you, everybody needs this set of materials. So each pair, or if you're sitting with three people and your partner's gone, then you can work as a group of three. But each group needs one mini whiteboard, which you find on my bookshelf, one little marker, and one eraser. And you can use those red rags if you run out of erasers. The sub will pause the video here and let you go get those materials. Okay, let's start with this first example. It says, first, identify the independent variable in this graph. Take a second with your partner, talk. What independent variable do you see here? To me, whenever I'm thinking, what is the independent variable, the first place I'm going to look is the x-axis, because that's where it's supposed to be. So I look down here, number of mentions in books. That does seem like the independent variable, the thing that changed. So that's my independent variable. Similarly, the dependent variable, the first place I'm going to look is the y-axis, which is labeled screen time in films. All right, so I'll put that there. Now, with your partner, what I'd like you to do is identify a pattern, a trend, or a relationship. Remember, the examples we have to work with are positive, negative, constant, or no relationship. Those are the four options you have. So take a look at this and see if you can identify some kind of pattern or relationship. When I look at this, it seems to be very clearly positive. The more times a character is mentioned in the book, it seems that they tend to have more screen time in the movies. So it's a positive relationship. This next one says make a prediction, which is kind of similar, right? If there is a relationship, then you can make a prediction. You can say the more times a character is mentioned in the book, the more screen time they're probably going to get. And that would be valid based on this data. Last part here says how credible is the source. I put this here just because it's good practice to think if you're ever presented with data that you yourself didn't collect. It's good to think, did this come from a reputable place? Is this valid data, or is this kind of sketchy? Do I think somebody may have made this up? When I look down here, it says the source is IMDb. If you don't know what that stands for, it stands for International Movie Database, which is a pretty good source of data for stuff like this. So I would say this is pretty relevant. Okay, let's try another example. This time, I'm going to let you and your partner identify all the variables by yourself, and I'm going to let you identify these three things down here as well. I'll give you a minute, 1 minute to look at those, and we'll come back in 1 minute. Your time starts now. You have 10 more seconds. All right, and that's time. So the independent variable. Well, we want to look at the x-axis. That's where it's supposed to be. When we look at the x-axis, it isn't actually very clearly labeled. Chart R is not the label of this graph. It's the website where I got this graph from. So that's kind of a red flag. It isn't labeled. We should always label our axes. So we can see that the thing that extends horizontally on the x-axis is this percentage, which I believe is actually labeled over here as user age breakdown, meaning a certain percentage of users fall within that age range. If you're like me, you're thinking, that doesn't seem like the thing that I am manipulating. Instead, what seems like the thing that's being manipulated is the age range, not the percentage of the users. So I chose this graph on purpose because I don't think it's very good. I think that this graph should be rotated 90 degrees. So that these age brackets over here are actually on the x-axis, and these bars extend up vertically. To me, that is a better graph. That is more intuitive to read. That making so to answer the questions, the independent variable is the thing that's being changed, manipulated. That's actually this age. The dependent variable, or what's responding to that, is the percentage of users. So even though they're in the wrong place, I chose this graph because I think it's a, kind of a bad example of a graph. Pattern of relationship, I think there's a lot to get here. The obvious one, I think, is as your age gets bigger, you tend to not use these two social media platforms as much. But you could have seen other things. You could have said maybe younger ages tend to use TikTok more than Facebook, whereas older ages tend to use Facebook more than TikTok. So those are some other patterns and relationships there. Predictions, same thing. If you fall within a certain age bracket, I can probably make a good prediction that you're more likely to use one of these platforms over the other. How credible is the source? Well, if you notice, there isn't a source listed. That is a red flag. We should always be skeptical if there's no source. Now there is a source. I cropped it out just so that I could talk about that. But if there's not a source listed, that's a red flag. We should be cautious of that. Here's another example. Let's do the same thing. Talk with your partners. Here are the questions, and write down these answers on your whiteboards. And we'll come back in a minute or two. I'll let the sub pause the video because I'm going to keep talking so I can get this video done in a reasonable amount of time. Okay. You should have looked at this graph with your partner and decided on answers to these questions. Independent variable, I think, is pretty obvious. It's games played. Dependent variable would be career NBA points scored. What would you title this graph, right? Remember, this is not really we don't want to be like really, quirky and creative here. I know that sounds bad, but we want to stick to a rule because that's going to make sure that whoever reads our graph knows what's happening. So we want to title it according to the rule, which is dependent versus independent, or Y versus X. So we should have titled it NBA points scored versus games played. Number 3, the pattern or relationship is, I think it's pretty clearly obvious, which makes sense. The more games you play, the more points you score. 4 says, what inferences can you make? So I think when it says inferences, right, excuse me, obviously the more games you play, the more points you score, but I don't think that's what the graph is actually trying to show us. One of the things I noticed when looking at the graph is this line here that says 30 points per game line, and how all of these dots fall underneath it, except for 2. There are 2 dots that are above that line, meaning that these players throughout their entire career scored more than 30 points per game. And obviously one of them is kind of highlighted in red, that being Michael Jordan. Michael Jordan didn't score the most total points ever. That would be, actually, this graph is outdated. This graph shows Kareem Abdul-Jabbar as that, but actually LeBron James has broken that record since this graph was made. But Michael Jordan also didn't play the most games. That's this person, whoever that is. But that's not the point of the graph. The point of the graph is, I think, trying to highlight a unique statistic for Michael Jordan as being one of the few to have more than 30 points per game. So that's an inference I made. 5 is the source credible. Well, NBA.com does seem like a good place for this data. Here's the actual title of the graph. Okay. Let's do another example here. Same thing, look at this with your partners, write down your answers on the whiteboard. The sub will pause the video and then unpause it when you are all done. After looking at this graph, independent seems to be day or maybe time or week. Actually, it looks like it's broken up by week, so any of those are fine. The dependent variable seems to be Google search volume. Number 2, we should title the graph, again, Y versus X. So Google search volume versus time. The trend or the relationship I see is different than what we've seen before. It seems to spike and then dip, and spike and dip, and spike and dip, but it seems very repetitive. It seems to do that over and over again. So as far as what is the relationship, I think the best relationship that suits this graph is a constant relationship. Like I said before, constant doesn't necessarily mean that every single data point is exactly identical. It just means that it might fluctuate, but it tends to do the same thing over and over again over the span of this X variable, which this seems to do. So I would call this a constant relationship. Number 4 says, what inferences can you make? Well, it seems interesting. They've highlighted in blue here the weekend, Saturday and Sunday, and it seems that the Google search volume really goes up on the weekends and dips during the week. So it makes me wonder, are people really using Google that much more on the weekends? Because I think about my own experience, I don't think I use Google that much more on the weekends. Um, so it kind of leaves me questioning a few things. I'm not sure exactly what inferences I'm supposed to make from this graph. 5 says, is the source of the data credible? It is, it's Google Trends, but I'm still stuck on this inferences. I'm going to show you the title of this graph, and I want you to tell me if you think a pretty key piece of information was omitted from the graph itself. Makes me giggle every time. Clearly, when we go back to the graph, it says Google search volume, but it never specified what the Google search was for. I was led to assume it was total Google searches, but clearly it wasn't. This is a specific Google search for a hangover cure. So that makes me think maybe another inference I can make is, when do people tend to do most of their drinking? I would say probably Fridays and Saturdays, because they do all their drinking on Fridays and Saturdays, and then they need to Google what's a hangover cure on Saturday and Sunday. I thought this was kind of a humorous graph. A couple more examples here. Same thing. Talk with your partner, answer the questions. This up will pause the video and then unpause it when you are done. All right, number 1, independent is years before present day, so time again. Dependent is carbon dioxide in parts per million. Title of the graph should be carbon dioxide in parts per million versus years before present day. The trend or the pattern, again, seems to be somewhat repetitive over time. So at least this portion seems to be pretty constant, except for right over here. That seems to be a very, very steep increase that had never been seen before. So I'd call that portion at least positive. Number 4, inferences, same thing. It seems like carbon dioxide levels over time have been pretty constant with some fluctuations, except for recent history. Recent history seems to be breaking the trend. The source of data is the National Oceanic Administration there, and climate.gov, and those are very reputable sources for this kind of data. Here's the actual title of the graph. Okay, let's do one more example, and then we will call it a day. Do the same thing, talk with your partner, and decide on each of the answers to each of these questions. I'm trying to move my face out of the way. Okay, number 1, independent variable seems to be year. It's not labeled very well, but I hope you can tell that these are years. Dependent variable seems to be, it's labeled as percent, but you can see here it's romantic comedies' share of box office ticket sales. So, 10% of the box office, that would be the dependent variable. So in terms of titling it, I would say maybe box office ticket share versus year. Number 3, the pattern seems to be overall negative. As time goes on, the share of box office ticket sales that these romantic comedies had is generally lowering. Inferences are, apparently rom-coms aren't very popular anymore. Source of data, is it credible? It just says the numbers. So that's kind of vague. I've never heard of that. That's something I would probably want to look into. Is the numbers a credible source? I don't even know what it is. Is that something we could do if we had some time for that? And lastly, here's the actual title of that graph. Oops. Okay, that will probably do it for today. Thank you for behaving for the sub, for participating. Hopefully I'm back tomorrow. COVID's kind of a funny thing. It lasts longer than other illnesses. So I hope to see you again soon. And thanks very much.